All right, so just to go back, we were talking about probability concepts from for midterm 2. Remember that the midterm 2 kinds of embraces counting, so you will have to study at least the recap for midterm 1 if you want to go at least do 1/3 of the test. So we saw the basic concepts, we saw formulas for the union, we saw that formula of the intersection with the complement. We learned about mutually exclusive events. Then we saw probability trees, which kinds of encapsulates all the concepts. You can solve problems both ways, right? Then last lecture, we talked about what we call equiprobable sample spaces, where we will calculate the probabilities. So we learned that in equiprobable sample spaces, the way we calculate probability is a ratio, right? It's a ratio of the outcomes of interest of that event divided by the total outcomes, okay? And even for conditional probabilities, when you're inside an equiprobable sample space, it turns out that you can break the calculation into two counting problems and a ratio between them. So the number of outcomes of the intersection divided by the number of outcomes of what came first. Okay? Then we solved some problems, some easy ones like the number of subsets, the probability of a particular subset. We solve a little bit more difficult that we had to remember the counting, the grouping, or the indistinguishability. So it's good to know that you will have to know this. And we finished with a exercise on again, counting problems, right? So it's a ratio of counting problems where you had people to sit around a table, okay? All right, so now let's oh, yeah, we also did the Bayes theorem, okay? So Bayes theorem is that one that you have two or more ways to get to an event, and you want to know what's the probability of a particular path. So you just take the path that you're interested, divide by the sum of all the other paths that you could have gotten there. Okay. Now we're going to end this recap with concept number 9, which is repeated trials. Actually, 9 and 10, repeated trials. Okay. So repeated trials are experiments that you do repeatedly. Well, it makes sense, right? Like you will do the experiments repeatedly. And every time you do the experiment, okay, you will have the same outcome. So, for example, if you're tossing a coin 10 times, well, 10 times. So the first tossing will have two outputs, heads or tails. The second tossing, heads or tails, and so on, right? So every time, every layer of your tree, if you're imagining a tree, will be the same, right? Like you have the same outcomes at each layer. You're just repeating the experiment. There's a particular case of repeated trials where you have two outcomes. So for example, this one where you toss the coin, okay? And we learned that if we want to find the probability of having a event, or like, for example, heads, exactly k times in n trials. So for example, what's the probability of having heads exactly 5 times in 11 trials? Okay? Meaning that I'm tossing the coin 11 times. So I toss the first time, second time, third time, 11 times. What's the probability of a particular outcome, which in this case is heads, turn out to be turns up 5 times? Okay, and we learned that there's a formula. Let's try to reason the formula again so that we don't have to memorize it completely. If I want 5 times, yeah.
When we're looking at repeated trials, is it always going to say like exactly however many times or something like that?
No.
Or like if this happens every 3 times, something like
Yeah,
that?
we will. In the end of the day, you will use the calculation of the exactly, right? But sometimes the wording is at least, no more than, and we will do an exercise.
But like it's looking for like a specific
Yeah.
element appearing however many times.
Exactly. So the probability that you're calculating with this formula is the probability of finding something exactly a number of times, right? So if in this case, if you're trying to find heads, let's not say 5. Let's make it 2 just to be easier. This means that you will have lots of possibilities. This one is a possibility. This one is a possibility, right? So, and there will be others because there I just draw 3 trials and there's 11. But in the end of the day, the probability of heads, right? Like it's a half here. The trees will always repeats itself like this. Okay? The probability of heads will have to appear 2 times in the branch that you're selecting, right? So the formula is this: the probability of heads happening, has to appear 2 times. So it will be a half times a half. It doesn't matter where's the sequence. It will be a half times a half times the probability of the other outcome happens. Okay, let me call just P. The P probability of heads is just P, just to ease a little bit the notation. So let's call P as the prob of heads. So in the end of the day, if you want 2 heads to happen, you will have to have 2 multiplications of heads. And the other probability for the other event, which is tails, given by 1 minus P, right, will appear the rest of the times. So 11 minus 2, which is 9. Okay? This is part of the formula. So just to recap, if you want to find heads 2 times, you will see the branches heads 2 times, so they will multiply. So you will have a square. And the other branches, for example, tails, will have its particular probability, which is given by 1 minus P, the rest of the times, 9 times. Okay? Well, this is not the complete formula. We're missing something. We're missing something that comes here in front of it. And it's based on the fact that I don't care where the heads come up. The 2 heads can come up just only on the 2 last trials. They can come on the 2 first. They can come in the 1st and then the 10th. It doesn't matter where the 2 heads happen. So what I'm going to do is, what I am actually doing is I am grouping the 11 trials, the n trials, which is 11. Okay, so let me put this way, 11 trials, into 2 of them being heads. Okay, and I mixed up the notation here. Let me put a half as the probability of this one, a half of the probability of this one too. Okay. So this is the formula. Okay? This is the formula for, like, we reason the formula, and we can do this whatever experiment we're talking about. It will be n. You'll have n trials that you will select to be an outcome times the probability of that outcome times the probability of the other outcome, n minus k. So this is the formula. Okay? So just so, yeah. It's to the power of 2, yeah. This is to the power of 2. Yeah, it's 0.5 times 0.5, right? Which is the same thing as 0.5 to the power of 2. Okay, so let's do this exercise here. So that we know how the questions about this are asked. So this is 2024 as well. In a routine chemical experiment, 70% of the time, there will be an endothermic reaction. So 70% of the time, something will happen, an event of interest will happen. This experiment is being performed 12 times. Okay? So I'm performing an experiment that can have a reaction or not have a reaction, right? And I'm doing it 12 times. Okay, so in theory, if I'm repeating the experiment, so I have the reaction or the endothermic reaction, or I don't have a reaction, and so on. And I keep repeating this, okay, for how many layers? For 12 layers. 12 layers or 12 trials. Okay. So if I were to ask you how many times the endothermic reaction, what's the probability of an endothermic reaction happens twice, you would directly apply the formula, right? Because I'm asking what's the chance of something happening exactly a number of times. But that would be too good to be true. The way we ask this is like this. What is the probability that there will be a reaction at least twice? So you have to think a little bit about what you have to do. It's not a direct application of the formula. Okay? So let's think about this. What does it mean to have a thing happening at least twice?
It happens no less than twice, but might happen more.
Yeah, exactly. So you have the endothermic reaction can happen exactly 2 times. It can happen 3 times, right? It can happen 4 times, and it can happen 12 times, right? So that's what you're talking about. So what you could do, and this is if it were an open question, I would consider it right, but it will be so much work, is to apply the formula for the number of times the event happened for 2 times, plus the probability that this event happened 2 times, exactly 2 times, plus the probability of this event happening exactly 3 times, plus, and so on. So you would have 10 terms, 10 different terms of this form here, of this binomial kind of form, right? Usually, and if you'll remember midterm 1, if you have a question that involves too many items, your brain should think about doing the opposite, right? Doing the opposite. So what does that mean? It means that what cannot happen? What is not of my interest? Well, it's this, right? It's the event not happening, and the event happening 1 time, right? This is not something that I don't want to happen. Okay? So one way to, easier way, so again, if you do the more work way, like the more longer answer in the open questions, that's fine. It will take you some time. But if you remember the counting the opposite, this will be less work for you. Okay? So what is the probability that we're trying to find? Well, the probability is this. This is all the situations that can happen. This represents a probability of 1, right? Something inside of this will happen. Okay? Either it will happen 0 times, 1 times, 2 times, 3 times, or 12 times. But I don't want this here to happen. So the probability of having all of this is actually 1 minus the probability of the square events happening. So 1 minus the probability of the endothermic reaction happens 0 times. Not put equal here. I'm having problems with the nomenclature today. So this is ER 0 times, right? And the probability of ER happening 1 time. Exactly 0 time, exactly 1 time. Do you agree? So now you can use the formula, but you will use the formula only twice, right? Only for the exactly 0 time and exactly 1 time. Because if you have this probability here, let's say, I don't know what it is, but let's say it's 0.2, the other part will be 0.8, right? Because they have to sum up to 1. Yeah. Yeah, so you want the probability of the arrows happening, right? This here. Okay, or let me put this in red. You want this probability, right? But you have 2 situations that are not of interest. Remember the pregnant and non-pregnant thing? So imagine that these situations here are the pregnant. It's of your interest. And these situations are the not pregnant. Okay? What do I know? I know that pregnant plus not pregnant should be equal to 1, right? So the probability, so 1 needs to be the probability of the red part plus the probability of blue, right? Which one you want? You want the probability of red, right? So the probability of red, if you isolate this, will be 1. Take this probability of blue to the other side, minus the probability of blue. Okay? What is the probability of blue? Well, the probability of blue are both these situations here. So the probability of blue is the probability of the reaction happening 0 times, exactly 0 times, plus the probability of the reaction happening 1 time. Okay? Good? All right, so I'm going to get rid of this. Better. Okay. So this is the red part. This is what I'm interested in. This is the part that is blue. And they have to sum up to 1. So let's calculate this. Well, the probability of 1 minus, what's the probability of having something happening 0 times? Well, you have the probability of that thing happening, which is 70%. how many times it will appear if it appears 0 times? It won't appear, right? It won't appear. So this won't appear. It will appear 0 times. Right? Times the probability of the other event happening. What's the other event? It's not having the reaction. If I had the reaction 0 times, how many times will 0.3 appear? All the others, right? So 12. Okay? Yeah.
I'm confused. Where did we get the 0.3?
It's, yeah, cool. So if the reaction has a chance of happening of 0.7, the not happening, so if this is 0.7, the other one needs to be 0.3, right? So if your endothermic reaction happens with 70% chance, the chance of not happening is just 30%.
But aren't we adding to it just happening once?
No, we're doing this first part here. When the endothermic reaction happens 0 times. So we're taking 0.7, won't appear actually, because you would have a branch, a path of only not happening the reaction. So this would appear 0 times, and actually the 0.3 would appear 12 times. All of the branches would be non-reaction. Okay? But this is not the answer. The answer is we have to put the binomial in front. And we have 12 trials selecting 0 to be endothermic reaction. Okay? All right. What else? Well, I will discount. So minus the probability of 0 times, minus the probability of 1 time, right? Because this minus goes inside the brackets. So what's the probability of having this 1 time? Well, you take the 0.7, and the 0.7 will appear 1 time, just once. For example, it would be this first branch, and then it would continue non-reaction. Okay? So the 0.7 will appear just 1 time, because just only 1 ER appeared. The rest of the branches will be what? NR. So it will be the other probability, which is 1 minus 0.7, appearing how many times? 11. Because 1 time it appeared the reaction, what's left will be non-reactive. Okay? And then we have the multinomial notation. Binomial notation. And I'm selecting 12 trials for 1 to be reactive. Okay? Now, if you take a look at the options here, you can see that this one is you have to have 1 minus 2 terms, right? So 1 minus 2 terms, it has to be this one. It's the only one that has this, but it's not matching completely, right? Actually, it's matching completely, because you have to remember that 12 choose 0. 12 choose 0, this notation in the binomial 12, 0, means the number of ways you can take 12 things, right? The number of ways you can choose 0 from 12 things. Well, what's the way to do that? It's just do nothing. Don't choose. It's just one way. Just don't do nothing, right? So 12 choose 0 is 1. So it matches here exactly. Okay? 0.7 to the power of 0 is also 1. So in the end of the day, the second parcel here is exactly this. It's just 0.3 to the 12. Okay? Yeah.
I'm confused. If the formula we wrote above, we're adding them, why when we carry it out does it turn into subtraction?
Yeah, you're summing, but you have this minus in front of the parenthesis.
In the middle you wrote subtraction, like between, like I see 1
It's just when you distribute this sign, it will be minus the first term minus the second one. So it's just a way to it's just to kind of group these two situations, but you're negating them. So you have to negate the first one and then the second one. Okay? Yeah.
But if we wanted to keep it in the way that you wrote,
Yeah.
you wrote it out, that's fine too.
Fine.
Because to make it a plus, we just have to put the brackets in, right?
Yeah.
Because that, it's simpler to me in my head, so if I just want to do it that way, that's fine.
Yeah.
Okay.
So this is 1 minus 0.3 to the 12 minus 12 choose 1 is how many ways can you choose one thing from 12? Well, just select 12 different things, right? So you will select first the number 1. This is one way. Then you will select number 2. This is another way of selecting one thing amongst 12. So you have 12 possibilities. So this here is 12. And it exactly matches this here. Okay. So just to answer the question before that, it was, oh, will they always ask exactly? No. Usually they won't ask exactly. They will ask what at least, at most. And you will have to think with what exactly situations you kind of go towards the answer. Yeah.
But at most, like, what would you do that?
If it would asking at most 2, like at most twice, then what interests you is 0 and 1.
Oh, like the same as at least.
No, at least is the red part, right? At most is the blue part.
So you wouldn't do the same.
You didn't need to do 1 minus that. You just answer the 2 terms here. Okay? So remember, at most is smaller than or equal, right? And at least is bigger than. Okay? All right. Questions? You will have at least 2 questions like this. You will have. Okay, so this is being recorded. Go through it again. Practice at home. Take other tests, other years, past years, because you will have something like this in the test. Yeah.
If we were looking through like the problem sets that are posted, like with the videos, would it be called repeated trials there too?
Yeah.
Okay.
Repeated trials. But as I said before, like the quizzes and the homeworks, like the worked videos, they are slightly more difficult than the tests, right? So I always suggest studying through the tests because the type of exercises are always the same. It changes just a little bit, and it's a little bit easier than the quizzes. There are questions in the quizzes that are way more complicated than we see here, right? And I really don't know why, but it's just that way, okay? All right. There's another item that we need to do recap, and this is the last item. Thank God, right? And this is repeated. How do you? Oh my God, repeat. That's right? Repeated trials with multiple outcomes. All right. So this is the last item from our recap. Okay. So repeated trials with multiple outcomes. It's the same thing, right? Like we repeat the experiment, but now it's just not heads or tails or reaction, not reaction. It's actually A, B, C, D, how many outcomes you have in that experiment will repeat itself. And I'm not going to go through all the tree thing and everything, but the way to tackle the problem is this. The probability of one of the outcomes coming out will repeat itself K1 times. The probability of the second outcomes K2 times. Probability of the third outcome K3 times. Oops. And you're actually grouping n trials into K1 to be the first outcome, K2 times to be the second outcome, K3 times to be the third outcome. So the question is, this is the answer for this question. What's the probability that in n trials, in n trials, what's the probability that the outcome 1 comes out exactly K1 times, outcome 2 comes out exactly K2 times, outcome 3 comes out exactly K3 times, and so on. Okay? So the question, what you're calculating with this formula is this: in n trials that are repeating, what's the probability of having exactly K1 times of outcome 1, K2 times of outcome 2, K3 times of outcome 3. Okay? That's you will use this formula to answer this exact question. Cool? All right. So now we can answer the other exercise. So let's do it. A simple four-sided die. Okay. I can't imagine. Is weighted such that it comes up 1 10% of the time, 2 20% of the time, 3 30% of the time, and comes up 4 40% of the time. So it's just, okay. So it's not an equiprobable sample space, it's not a fair sample space, but that's fine. Like, we're not calculating the probabilities. The probabilities are given to us, right? They engineered the four-sided die to the face that has has number 4 to be 4 times the weight of number 1. So the probability of turning up is 4 times bigger, right? So it doesn't matter. They did that. You have the probabilities. If this die is rolled 10 times, okay, what's the probability that 4 comes up 4 times as often as 1, and 3 is rolled exactly 3 times? Okay, so you're reading it. You know the probabilities. You know that this is a repeated trial because you're told that. You're going to repeat this 10 times. Okay? Now, what's the question? Let's break up the question. Now, the question is this: what's the probability that 4 comes up 4 times as often as 1, and 3 is rolled exactly 3 times? So the probability of 3 being showing up exactly 3 times, right? And 4 coming up 4 times more then 1. This is what's being asked. So you're going to roll the thing 10 times, right? The question is, I'm interested in an event, in events where the number 3 comes up 3 times. That's easy, like to imagine. The other event that should happen at the same time, because it's an n, is the number 4 should come up 4 times more than number 1. That's what's being asked, okay? There's no way you could directly apply any formula if you don't think about the problem, right? What are the situations that interest you, okay? Because in repeated trial, the only way we know how to answer a question is the exactly amount, right? And this is not there yet. So we have to work ourselves through this and try to then imagine what kinds of situations, exact situations that we want. So you have 10 trials. This is my die. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 die. Okay? 10 die, trials. So one situation that would be fine for me is this. Well, 3 appears 3 times. This is one possible situation, okay? But the event that I'm interested is not only 3 times of 3, it's actually 4 coming up 4 times more than 1. So meaning that if 1 happened 1 time, what should happen with 4? It should appear 4 times. So it would appear 4, and then here 4, 4, and 4. This is a situation that interests me, okay? What other situation could happen that has this rule? Well, let's see. Three happening 3 times, okay? I'm just making it up where, like, the sequence just happened 3 times. The first 3 times it was 3. That's awesome. The other thing that can happen is not having a 1, right? Because if I had 2 1s, right, 4 would have to happen 8 times. And so this situation here cannot happen. 1 appearing 2 times cannot happen. 1 appearing 3 times cannot happen. So 1 is limited to appear 1 time. Do you agree? Or 0 times, right? If 1 don't appear, then, well, 4 doesn't appear too. But it's fact that it's 4 times 0 is 4 times more than 0, right? So if 1 doesn't appear, the rest of the situations will be 2, right? Because 1 and 4 won't appear. So this is also a situation that I'm satisfied with. Okay? So, but here's the thing. I kind of completed this in these positions, but do you agree that it doesn't matter the order, right? So now we can do, well, you know what? It doesn't matter the order. What I want, this probability, is actually the probability of having exactly 1, I don't care the order, and exactly 4 4s, and exactly 3 3s, right? And exactly 2 2s. That's the first situation. Plus the probability of having exactly 0 1s and exactly 0 4s and exactly 0 3s, 3 3s, and how many 2s? 1, 2, 3, 4, 5, 6, 6, right? 7, Yeah. Yeah, 7. And I'm out of thing. 7 twos. Okay? So one way I like to solve this is like this. I do when I have too many variables in multiple outcomes, I like to make myself a table. It helps. So these are the faces of the die and the number of times it will appear. Okay? I have two situations that are good for me. The first one, recall, is 1 appearing 1 time. Then 4 will appear 4 times. 3 is 3, right? And 2 is left with 2. Right? The other situation is this don't appear, this don't appear, this appear 3 times, and this appear 7 times. Okay? So now I know that my probability is that as these two situations where I have the exact amount of times each face comes up. Right? So this is the face of the die. These are the faces. This are the number of times each one appear. So let's do this first. I have 10 trials. I'm selecting 1 trial to be 1, 2 trials to be 2, 3 trials to be 3, 4 trials to be 4. It doesn't matter the order. This is a grouping. Awesome. Now, if 1 appears 1 time, what's the probability how many times the probability of 1 will appear in the tree? Just 1, right? It's 10%. The 10% of number 1 will appear just once. The 20% of number 2 will appear how many times? 2. The 30% of number 3 will appear how many times? And finally, the 40% of number 4 will appear 4 times. This is this first situation. Okay? Now the second situation, plus second situations, you have 10 trials. 0 will be chosen to be 1, 7 to be 2, 3 to be 3, 0 to be 4. How many times the number 1 will appear? 0. So the probability, if you imagine the tree, you don't have that probability in your path because it's not appearing. So it's 0. How many times you have the probability of 2 appear? Well, the probability 2 is appearing 7 times. So when you're multiplying to go through the path, you will have 7.2s, right? How many times 0.3 will appear? 3, right? And 4 won't appear, so that's this. And if you go to the here is the answer. So you choose 10 to 1, 2, 3, 4, exactly the first this here, okay? 0, 1, 2, 3, 4, and then don't appear 1, appear 2 7 times, appear 3 3 times, appear 4 0 times. Okay? Questions? Yeah.
Is there some kind
I'm
of
old.
answer option where the 0.1 to the power of 0 and stuff like that is simplified?
Yeah, it could happen. Yeah, it can happen. Unfortunately, yeah.
Is it only when there's multiple outcomes that we see it asking for something happening like 4 times as often, or can that just happen with multiple, like the repeated trials in general?
You can have just a repeated trials with 2 outcomes, and for example, you could have an unfair coin, right? Like where the heads occurs 4 times more often than tails, right? So that's possible. Okay. All right, that's it. We are done. And I just want to work out a final exercise. It's an open question from last year. And it's every year. So it's something that it's worth for us to work on. Okay? And it's about trees. So we don't need to recap anything. We're done with the recap. 10 items of probability that you should know to get the test done. Okay? Now let's do this exercise here. Erica plays fantasy video games on her computer every Friday night. Lately, she's been playing two popular games, Draconian Quest and Eternal Vampire, Rise of Lissa. When she plays Draconian Quest, she wins the game 40% of the time. Okay? And when Erica plays Eternal Vampire, she has a 70% chance win rate. Okay? So think about a tree. Erica can go and play Draconian Quest or Eternal Vampire. And obviously, she can win or lose both games, right? The information that is given to you is that when she plays Draconian Quest, she has a 40% time of chance of winning, meaning that this is the conditional probability, right? So given that I played Draconia Quest, right, I have a 40% chance of winning. So this branch here, which is the conditional, will receive a 0.4 value. And the other information is that when she plays the Eternal Vampire, Rise of Lissa, she has a win rate of 75. So this is the other conditional probability. Okay? Meaning that given that she's playing Eternal Vampire, she wins 75% of the times, okay? All right, so that's all the information, I guess. Let me see. Erica has been playing Draconia Quest 4 times as often as she's been playing Eternal Vampire. So what does that mean? Well, when she's going to choose a game, when she's here in this first node here, she has 2 options. She can choose Draconia or Eternal. But it is given to you that she goes to Draconia 4 times as often. So think about this. If this is X, this is 4X, right? So if the probability of going to Eternal is X, I'm telling you that actually she's going more towards the Draconian 4 times more than X, right? So it's kind of hidden. The information is given to you, but it's hidden because we know that 4X plus X needs to be equal to 1. So 5X is 1, X is 1 over 5, which is 0.2. In the end of the day, this X is 0.2 and this is 0.8. Okay? So the first item of the question, this is the open question. First, B1, it's the open question for midterm 2 2024, last fall. So the first question was fill in the following probability tree to represent the possible outcomes. So it's just doing the tree. And we have it all to kind of complete the tree. Why? Well, we have 0, 8, we have 0, 2. If we have 0, 4, how much has to be here? 0, 6. If I have 0, 75, how much has to be here? 0.25. This question here is worth 3 points. So, and letter A is 2 points. So just by completing the tree, you would mark 2 points in your test. Yeah.
I missed how you got the 0.8 and 0.2 for Z.
Yeah. So did you see that they told you that Erica goes to D 4 times more?
Yeah.
So whatever number it is the probability to go to E, going to D is 4 times more. So it's 4x, right? So if this number here is x, the number on the top branch is 4x.
Okay, I get that. How did we get 0.2?
So there's a property of the tree that says that each branch has to sum up to 1, right?
Okay.
So when we do x plus 4x equal to 1, you can solve for x. So 4x plus x is 5x, right? So you have 4 times x plus 1 times x. 4 times apples, 4 apples plus 1 apple is 5 apples, so it's 5x equal to 1. And you solve for x. So you divide 1 by 5. 1 by 5 is 0.2.
Okay.
So I found the x. And given that the upper branch is 4x, this will be 4 times 0.02. Okay? Now the question B is this: what is the probability that Erica wins whatever games she ends up playing? So what's the probability of win? Whatever game, right? Well, if you know trees, the probability of some event is the paths that pass or goes to your event, right? So it's just the answer to this exercise is just summing up both paths. So 4.8 times 0.4 is the first path, plus 0.2 times 0.75, it's the second path. And this question is worth 3 points. This is the type of open question you should not miss, because it's 3 points. Okay? It's not a difficult question. You just have to complete a tree and find 2 paths, right? This kinds of questions repeats itself a lot. So be sure to recap trees, to know how to populate a tree, because if you know at least how to populate the tree, you will make at least 2 marks. Okay? Good? So good luck into studying for midterm 2. Next lecture we will change subject, okay?